Today we are going to talk about finding the length of a curve. So we're going to have bells in the middle of this, but that's okay. Bells are fine. Now, this is the first BC topic that we have come to, but it's not that difficult. It is mostly done on the calculator just because of the way that the formula is set up, okay? Now, we have talked about area under a curve. So let's kind of review for a minute. Where is my other pen? Here it is. We have a first quadrant and we have a curve. We're going to say that A is here and B is here, and we want to find the area under that curve. Now, to estimate area under a curve from A to B, we use what? What did we use to estimate the area under a curve from A to B? No, before that. Before we learned integrals, what did we use? Riemann sums, which are really what shape? Rectangles or trapezoids, okay? So let's go back to review what this is all about. So let's say we have a rectangle right here. We use rectangles. Okay, kind of thinking back to the way we did volume. What is the formula for the area of a rectangle? Base times height. What is B? What is H? Now the base is not that B over there, it's a different B. Does anybody know what B is? The distance from A to the end of the rectangle, which we called a change in what? X. It is a change in X. We're going to call it delta X. Now the height of the rectangle is Y, which is f of x, right? So then we took that information and it became an integral when we added them all up, because remember, an integral is just a way to accumulate things. It adds up all the rectangles. So what are my limits of integration? A to B, where you start and stop making rectangles. And then we just put in here f of x dx. Now remember, the delta x is the dx. So f of x is the height, dx is the base. That creates the area of the rectangle, and the integral adds them all up. Okay? So we found each rectangle, then we added them all up with an integral. We're going to do something very similar to that, but with finding the length of a piece of curve. How long is that pink line, or that pink curve? Okay. Now, in the past, how do you find the length of something that's curved? You could get a piece of string and you lay it along there until you get it to fit, and then you take it off and you measure it, make it straight. We can do that without having to, we can find that without having to do that. So we're going to estimate the length of a curve by dividing the curve into, and I'm not going to tell you just yet, just write that much. We're going to estimate the length of the curve by dividing the curve into, if you cut a tiny piece of curve and you zoom it in really close, what would it look like? A little bitty what? It'd look like a line. Because linearization, don't we take a curve and zoom it in and we get a line? Yes? So we're basically going to take this curve and we're going to cut it into tiny line segments. So instead of rectangles, we're going to use line segments today. So what I want to do is I want to draw a piece of this curve zoomed in a lot. So here, just draw a little curve piece. And I'm going to estimate the length from here to here. Now, if you estimate the length, it would be straight. It's not exact, but it's close. Now, how do we find the length of straight pieces of line? What's the formula that we use? The distance formula, exactly. So we're going to use a variation on the distance formula, actually where the distance formula came from. We're going to construct a right triangle right here to find the length of that. Okay, I'm going to call this little piece of line C. I'm just going to call it C because it's like a hypotenuse. Okay, now if you look at this up here, think of me drawing the line connecting those two right there. What did we call the distance from this point to this point? That would match this down here. Delta x. So label this delta x. And what do you think this distance is going to be? It's not f of x. F of x goes from 0 to that point. This is actually a change in y. Think about it. From this point to this point, this is its change in x. This is its change in y to get from here to here.
Wasn't that slope?
It is kind of, yeah, it's slope. Change in y over change in x. You could think of it as slope. It's a great way to think of it. Okay, so now let's put this into the Pythagorean theorem. So, to find c, we would do c squared equals delta x squared plus delta y squared. Do you agree with that?
Mm-hmm.
Does that make sense?
Yeah.
Okay, we are going to finagle this equation to where we can take it and just like the base and height from a rectangle, we can put it into an integral and use it to find our length of our segments. So if I wanted to solve for just that one c, how long is that one c? What would I do? In other words, I would have to square root both sides, right? I was going to say, how do I get the c by itself? Take the square root of both sides. So it's the square root of delta x squared plus delta y squared. Now make sure that the delta x and delta y are in parentheses, please. It's very important that they are. Okay? Now, I can't put that into an integral yet because it's got two different variables. Remember, we can't have an integral with two variables. We've got to have it down to one. Okay? So what we're going to do is we're going to do a little bit of mathematical finagling. We're going to just rearrange this in a very unusual way, probably something you've never done before. But it's going to make this problem turn into something that's very easy to work. So, c is equal to, and now I'm going to make a very big square root sign because I'm going to have to end up with something bigger inside. I'm not going to tell you what it is yet. I am going to take this thing and I'm going to factor out delta x squared. Now you may be thinking to yourself, how can you do that? You don't have a delta x squared in both terms. Sometimes you can factor stuff out even if it doesn't appear in every term, if it helps you do what you need to do. Okay, so let's think for a minute. If I factor delta x squared out of this, what am I going to get? 1 plus. Does anybody have an idea of what this is going to be?
Change in y squared over change in x.
Exactly. It's going to be delta y squared over delta x squared. Extend your fraction bar. Because if you re-substitute the delta x squared in there, this delta x squared would cancel with it. Does that make sense?
Mm-hmm.
It's kind of some weird math, but it's helpful for what we're doing. Okay? Now, where we're going with this is the fact that delta y and delta x are the same thing as dy and dx. And what is dy over dx the same as?
Derivative.
The derivative. So it's turning it into a derivative. So please write this down. To sum up all of the line segments from A to B, we are going to integrate. We integrate. To sum up all the line segments from A to B, we're going to integrate. Now remember, this picture that I drew that's at the top of the screen right now, that's just one little piece of the graph. That's not the whole thing. It's 1 micron of the graph. And then I'm going to add them all up and make them as short as I possibly can. Make them so close together it's like one single dot. So that means we're going to have the integral from where to where? What do you think? A to B of each line segment C, which is delta x squared times 1 plus, now I'm going to make one big fraction, one big parentheses out of this, delta y over delta x squared, like so. Well, that doesn't look very good. Now I can change the one on the end to a derivative in a minute, but that delta x squared, it's actually going to come out of the radical. So this is going to be the length of a curve is equal to the integral from a to b. I need to close that parentheses again. So square root, leave the delta x off, 1 plus dy dx squared, and then the delta x squared comes out of the radical, and what does it become? What is the square root of delta x squared? Delta x, or dx. Remember in the original one we changed the delta x, the width, into a dx? Do the same thing here. Okay? So, another form of the answer is equal to the integral from a to b of the square root of 1 plus f prime of x dx. That looks more like the way we're going to see it, and that's probably the way you're going to think of it because our functions are given to us in terms of f prime. Yes, ma'am?
Wait, so dx and delta x are the same thing?
Yes. Dx and delta x are the same thing. Okay. So that is a formula that you need to memorize. Anytime you find the length of a curve, it's equal to the integral from a to b of the square root of 1 plus, I forgot something. What did I forget?
Oh, your parentheses on the first layer.
I forgot the squared. I did that last period too. Squared dx, very important. Yes?
Is that a parentheses on the end?
This is the parentheses for this.
Ah.
Yeah, these two go together. That's where I got that other parentheses. Okay, don't forget the squared like I just did. Okay, the square root of 1 plus the derivative squared. That's what you need to remember. Questions so far?
It's kind of a stupid question, but
Go ahead and ask.
with the whole square root over the 1 plus f prime of x squared,
Mm-hmm.
wouldn't that technically simplify to 1 plus f prime x?
That's a good question. That's a very good question. Okay. Question is, does the square root of 1 plus f prime of x, the quantity squared, just simplify to the square root, oh, not to the square root, but to 1 plus f prime of x? Can you take the square root of each part individually? Okay. Let me prove to you why it doesn't work. 1 is something squared, and that's why you think you can pull it out, and so is this. So let's change it all to numbers. If you have the square root of 3 squared plus 4 squared, does that equal 3 plus 4? It doesn't work, does it? 3 squared is 9, 4 squared is 16, that's the square root of 25 equals 7, and that's not true. See that? That's why you can't just pull out individual parts from an addition problem.
Can you put that little slash that says not equal?
Yes, I sure can.
Okay, thank you.
That's a great question, and something that a lot of people struggle with. But do you understand now why you can't just pull those out?
Yes.
But you can, however, if they're like things being multiplied.
If they're multiplied, yes you can. Let's try it with multiplication. The square root of 3 squared times 4 squared equals 3 times 4. Let's try this. The square root of 9 times 16 is 144. And what is 3 times 4? 12. Is that true? Now it sinks in. Okay. Very good question. I'm glad you asked it. If they're multiplied, you're good. If they're added, no way. Okay. Any other questions? All right. This packet that you received is off of mastermathmentor.com. I want to give him credit for it. Notice that the title, which you can't see right now, says arc length and area of surface of revolution. Arc length is what we just did. That is on the AP exam. Surface of revolution is not. My goal was to teach you both of them, but I'm just going to focus on arc length because first period was shorter today and I didn't have time to teach all of it to them. So we're just going to do the arc length, which is what you need to know for AP. Okay? He goes through a different explanation of how to get the formula, but if you look at the bottom of the page, this last line in the box, that's the exact same formula we just came up with. Y'all see that? L equals the integral from a to b of the square root of 1 plus f prime of x squared dx. Okay? That is the formula that we're going to be working with. Now, please flip this over on the back. Now, some of these problems, very few of these problems can be worked by hand. We're going to do a few by hand, and then we're going to do the majority of them on the calculator. That's why you need your calculator out. We're not going to do all of these. We're going to do a select few. So, take a look at number 2. It says find the exact length of y equals 5x minus 2 from x equals negative 1 to x equals 2. We're going to do it totally without a graph. Just do it using the formula we just found. Now, what kind of graph is this? It's a line. Could you find the length of a line without calculus? Yes. But I'm going to do it with calculus to show you that it can be done, and honestly the amount of work that it requires is about the same, if not less, if it's linear, okay? So, based on the formula, the length will be the integral from where to where? Negative 1 to 2 of the square root of 1 plus the derivative squared. What's the derivative of this?
5.
It's just 5. So it is going to be 5 squared dx. Now, unlike what we've been doing for the last week, volumes of revolution. Remember, sometimes it was dx and sometimes it was dy, and you always had to go and figure it out. Nice thing about this, it's always dx. Always. Okay? Because it's only one-dimensional. So, let's take this a step further. This will be the integral from negative 1 to 2 of the square root of what? 26 dx. Okay? Now, how do we do that? How do we take the integral of the square root of 26? Well, no, we're going to do this by hand.
Oh, okay, but you have to find the antiderivative.
You have to find the antiderivative of this. So what is the antiderivative of the square root of 26?
Oh, you have to do the 1/2.
Okay, but this is a constant, folks. Don't make it harder than it is.
Square root of 26x.
You just put an x on it, exactly. This equals the square root of 26x, just as if it was a 26. What if it had just been a plain 26? It'd just be 26x. Okay, now what do I do?
You plug it in.
Plug in the numbers, but I need to write my back bracket, negative 1 to 2. Which one goes in first?
2.
2. So that would be 2 square roots of 26, right? Minus negative 1 square root of 26 plus. So what do I get? How do you add those together? It's just 3 square root of 26. And that is the length of that piece of line from negative 1 to 2. That wasn't too hard. Once you remembered how to take the integral of the square root of 26, then you're good to go, right? Questions on that one? Pretty straightforward. Okay, we're not going to do number 3 for the interest of time. Now, some of the questions in the homework say do by hand. That's the only one we're going to do by hand. Everything else we're going to do on the calculator just to make life simpler We're going to talk a little bit about how you would do it by hand if you had to, but we're not going to force ourselves to do it. Okay. Now this is one that he says there are a few functions, only a few, other than linear, for which the arc length integral can be taken. One of these is the x to the 3 halves. Find the exact length of this curve from 0 to 4. And we're going to do it with the calculator. Okay, so L equals, what are my limits of integration? 0 to 4 of the square root 1 plus, okay, I'm supposed to put f prime squared in there. So what I'm going to do is I'm going to go out to the side because f prime is not quite as easy as it was for number 2, and do the math out to the side. So here's f of x equals x to the 3 halves. Because we go a lot back and forth between derivatives and integrals, please remember, derivatives drop powers and decrease, integrals increase. So I'm taking a derivative, so I drop the power down, 3 halves x to the 1 half. Is that it?
No.
Yes. There is, okay, well actually no, because the x is the inner, well the inner function is just an x, but its derivative is 1, so we don't need to worry about it. Okay? Now, I'm going to go ahead and square this here. F prime of x squared. I'm going to go ahead and square it over here and then stick it into the integral. So, when you square things that are multiplied, remember that you square each individual component. What is 3 halves squared? 9 over 4. You just square the top and square the bottom. So it's 9 over 4 x to the 1 half squared. And what is x to the 1 half squared? X to the first. So it's just 9/4 x, right? That's why this one comes out so nice. So 9/4 x goes in that radical with dx on the end. Because I've already put it in there and I've already squared it. Please keep track of when you square it. Okay, now let's talk for a minute about if we had to do this by hand. What rule would you need to use? Or how would you do this problem? Does it look like chain rule?
Yes.
Okay, now remember, when your brain says chain rule, it's U substitution when you go integrals. Derivatives is chain rule. Antiderivatives is U substitution. Okay? So I would have to do a U sub here. U would be the inside, and then du would be its derivative and go from there. Okay? But we're going to do this one on the calculator. So grab your calculator. Okay? We're going to do math 9. 0 to 4. When you put the square root bar will extend as far as you need it to. And it's the whole problem I'm going to need it for this time. 1 plus, I'm going to put the fraction bar, alpha y equals and enter, 9x over 4 dx. Okay? Is everybody good with that? Now remember, we already squared it, so we don't have to put a square on that. Push enter, and we get that the length of the curve is 9.073, and I'm writing a parenthesis 4 afterwards, and I want to talk about that. I have just enough time to do that. Okay? Your answers on the back of the worksheet that you will be getting later are going to look just like this. And the reason they do is this is how I make answer keys. You have to go 3 decimal places, but I need to check the 4th to see whether or not you are allowed to round that problem. So, is this one roundable?
No.
No, it's not. So the only correct answer would be 9.073. If I had a 7 in there, AP would accept 9.073 or 9.074. You follow what I'm saying? So as you check your answers on the back, if you do them all and then go back and check, just look at the last digit to decide whether or not you could have rounded it. Does that make sense? Yes?
But on the AP exam, we don't have to put the parentheses.
No, that's just for you to see and me to understand when I'm grading, okay? Yes, sir.
And they would rather do this than just straight, just rounded.
No, they don't want you to write this, okay? I'm just letting you know, this tells me that you could not round this one, that only 9.073 is allowed.
But if we can't round it, just round it.
You could round it if you want to. You can either round it or just cut it off, it's up to you. Okay, any questions on that? Okay, the answers are up here for those two problems. Again, I put the parentheses around the numbers so that you can know whether or not you're allowed to round on those two right there. So did we have good success on this? Are we all good? Okay, I want to jump back now to number 5. So let's take a look at number 5. And it says, at time t equals 0, a bug crawls along the path f of t equals 1/3 parentheses t squared plus 2 to the 3/2, t measured in seconds, and f of t measured in feet. Now, this is not straight line motion. He is actually crawling on a curve. So it's totally different when it comes to doing the problem than what we've done before. What is the average speed of the bug over the first 6 seconds? Now, I'll be honest with you. The first time I looked at this problem, having never seen it before, my brain said AROC, average rate of change. Does that make sense? But in this case, it doesn't work because this isn't really, it doesn't fit into the straight line motion way of doing things. We have to do this a little bit differently. We have to think of speed as distance over time. And the distance happens to be the length of the curve. It's the length of the curve over time is what we're going to have to do. Okay? So we're going to, because it's going along a curve, we have to find out how far he traveled on that curve, that's his distance, divided by the time. So the distance is going to be the integral from what to what? 0 to 6, very good, square root of 1 plus, I'm going to write the formula this time because I'm changing variables, f prime of t dt. But what did I forget? I was just checking to make sure you were paying attention. You know that anytime a teacher says that, they're lying because they actually forgot it themselves. Yeah. Okay. So what I'm going to do is come out to the side. This problem doesn't need that much room. I'm going to kind of come out in the middle here and do the work to do the derivative of this. Now I'm not going to recopy it. I'm just going to go straight to the derivative right here. What rule do I need to take the derivative of this function? I need the chain rule. So the first thing I do is bring the 3/2 down. What's 1/3 times 3/2? 3 over 6, which reduces to 1/2, parentheses to the 1/2 power. Remember, power drops, derivatives decrease. In the parentheses goes what? T squared plus 2 goes in here first, but then times 2t. Okay, I'm going to clean it up right now first before I square it. What can I get rid of? What can I cancel? The 1/2 and the 2. So f prime of t equals, I'm going to bring the t to the front, and then t squared plus 2 to the 1/2 power. Are you with me? Now I'm supposed to square this. So I'm going to square it now. So it's going to be t squared, and then this thing to the 1/2 squared. And so what would it be? Just t squared plus 2, agreed? With no power, with a power of 1. So when I come back over here and write my formula again, 0 to 6, it is going to be the square root of 1 plus t squared times t squared plus 2 dt Now, can you distribute that? D equals 0 to 6, square root of 1 plus, what's t squared times t squared? T to the 4th, remember, you add the exponents, plus 2t squared dt. Now, it's ready to go in the calculator. So I'll bring my calculator up. Can you see it? Yes. So math 9, 0 to 6, square root of 1 plus x to the 4th plus 2x squared out dx. Give you a chance to punch that in. And you get 78. Is that the answer?
No.
No. What did I just find?
The
The distance. And so what should I do with it?
divine speed.
To find the speed, I have to take that distance and divide it by the time. What is the amount of time that has elapsed? 6 seconds. So divided by 6 equals, and the answer is 13 feet per second. Because if you go back to the top, that's the units of measure that it tells you the problem is. Okay? Questions on that one? Anybody? Okay. Here we do the next one. It says, at what time k is the speed of the bug equal to the average speed over 6 seconds? Now, we actually found the AROC, but we can't use the AROC formula because of the way the function was defined. So this question is actually asking you a mean value theorem question. It's saying the speed of the bug at time k, that's IROC, when does that equal the average speed, AROC? Okay? So what I need to do is think for a minute. This right here, let me use another color. I just found that, didn't I? What I just underlined in pink, didn't I just find that number? What does it equal? 13. So I'm going to set something equal to 13. Does that make sense? So 13 equals the speed of the bug at time k.
Is it the derivative?
Yes. I'm going to take the derivative of the function and plug in k. That's the speed at time k. Now, speed is actually absolute value velocity, but once we're solving the problem, we will make sure we take the positive answer. That's how we take care of the absolute value. The speed of the bug is f prime of k. This right there is f prime of k. That's what it's asking. Now, did I already take the derivative of this thing? Yeah, right here. So it's k, bring this over here, k times k squared plus 2 to the 1/2 power. I already took the derivative. Don't reinvent the wheel. You already did it. Okay. Now, I have a square root and a k, but look what it says out to the side. Use a calculator. So how do we solve this problem if we're going to use a calculator?
Do you isolate k?
Not exactly. We move everything to one side of the problem and we set it equal to what? You want to set it equal to 0 so you can use the 0 function on the calculator. Okay? So let's move the 13 over with the k's. So 0 equals k times k squared plus 2 to the 1/2 minus 13. Now, I'm going to write it a different way, just for those of you who would prefer to put it in the calculator like this. I don't particularly care for fractional exponents. I'd rather write it as a radical. Okay, so now we're going to take the calculator and we're going to type this into y equals and find the answer. So I need to scoot this over so I have room for my calculator. Oops, I still don't have enough room. Move. There we go. All right, so we're going to clear this out. We're going to go to y equals, and we're going to type in x square root x squared plus 2. Make sure you right arrow to get out of the radical before you press the minus 13. Okay, remember I said always try zoom 4 first? Same thing applies here. So let's do zoom and 4. Well, I only see one crossing point. That's kind of nice. If we had a negative one, we would ignore it because it's speed. And it, well, actually, we're solving for time. I take that back. We're solving for time. So, do you remember what buttons to find to press to find the zeros? Second trace. Now, before you push trace, what two numbers is that crossing point between? 3 and 4. So second trace 0. It's somewhere between 3 as a left bound and 4 as a right bound. Just press enter for the guess and it gives you the answer. K equals 3.469 and the next digit is 6, so you could do 3.470 if you wanted to. Okay, so let's recap. We said we wanted to find where the speed of the bug at time k, which is the derivative at k, is equal to the answer we just got. So when you solve it and set it equal to 0 and do the zeros, you find that answer right there. Okay? Any questions?